An easy way to expand a binomial expression with a positive higher index is the use of a Pascal triangle. When we say a Pascal triangle, what it is? It is a type of triangle made up of numbers. Is that it? No, of course, there is more to it. What a Pascal triangle actually looks like, it looks like something like this. A set of numbers well arranged to form a particular triangle. Take a very good look at this type of triangle. Can you see any pattern in here? If yes, let us know. In the triangle, each number is the sum of the two numbers directly above it. Notice that 2 is the sum of 1 and 1. This 3 is the sum of 1 and 2. 3 is the sum of 2 and 1. 21 is the sum of 6 and 15, and so on. We have also seen that the starting and the ending numbers are always 1 in each row. Yes, all the numbers on the extreme left and on the extreme right are all 1. In Pascal triangles, the rows are numbers starting from 0. This is row 0. This is row 1. This is row 2, and so on. The third row is 1, 3, 3, 1. And the fifth row is 1, 5, 10, 10, 5, 1, and so on. Are you wondering why we need this triangle and what we do with it? You will get to know that soon. But before that, let's learn some interesting things about the Pascal triangle. What do you think about these two diagonals? Oh yes, they are the set of natural numbers. Who can help find more patterns? Check out these two diagonals. What could this possibly be? The numbers are 1, 3, 6, 10, 15, 21. For each number, let's imagine the same number of circles. Let's arrange them like this. We can see that for each number we can form equilateral triangles from the number of circles. Number of circles of 3 can be arranged like this. 6 can also be arranged like this, and so on. So the set of these numbers is called the set of triangular numbers. Interesting, right? Did you notice any other pattern? It could be anything. I want you to observe each row. What can you see? Let's see what happens when we add each numbers in a row of a Pascal triangle. Let's start by adding the numbers in the second row. Adding up these numbers gives us 4. Now, can you try adding the numbers in the third and the fourth row? The result is 8 and 16. We can see a pattern in these numbers: 4, 8, and 16. 4 can be written as 2 square, and 8, 2 cube, 16, 2 exponent 4, and so on. Let's generalize this pattern. The sum of the row can be represented by 2 raised to the number of the row. You can check it out for any row. For row 7, the sum will be equal to 128, which is 2 raised to 7. Are you still wondering how do we use this Pascal triangle in binomial theorem? Can you tell me the expansion of a plus b all square? It is a square plus 2ab plus b square. Looking at this binomial, what is the power of the binomial? It is 2, which is also known as index of the binomial. But before we continue, we have to know the binomial coefficients. Binomial coefficients are the coefficients in each term of the binomial expansion. Who can tell me what the binomial coefficients of a plus b all square are? They are 1, 2, 1. The number in the second row are the same as the number of binomial coefficients of the expansion with index 2. So what will be the expansion of a plus b all cube? It will be equal to a cube plus 3a square b plus 3a b square plus b cube. What is the coefficient here? It is 1, 3, 3, 1. All the numbers are the same as the third row of the Pascal triangle. From these, we can conclude that each row in the Pascal triangle gives us the binomial coefficient of the expansion in any binomial having a positive index.